Another fluid flow problem we have, this time we're not going to have a rectangular tank, but we're going to have a cylindrical tank, and it has a height of 9 meters and a radius of 3 meters as well. And if the tank is full of water, how much work is required to pump the water to the top of the tank and then out of the tank? So we're going to use 1,000 kilograms per cubic meter for the density and 9.8 meters per square second for the acceleration due to gravity. And then we're going to determine if it's true if it takes half as much work to pump the water out of the tank when it is half full, okay, as when it is full. Explain. All right, so first thing, let's go ahead and draw a diagram of this. All right, so we have a cylindrical tank, all right, and we know that the radius r is going to be equal to 3 meters, and the height h is going to be 9 meters. And we know that the work is going to be equal to 0 to the height, and we have our area in terms of y, right? And then also we're going to have some sort of density function, and then we're going to have the gravitational constant, and then h minus y dy, all right? So in this case, it's pretty obvious that h is 9, and so our limits of integration are going to go from 0 to 9. We're given that the density function, or the density of this, is going to be 1,000, right? It's constant, and then 9.8 meters per second square. So we just need the area. And what that means is we need a cross section. All right, so here's one, here's another, and it looks like that these are all circles of radius 3. And we remember that the area of a circle is pi r squared, but in this case, we know that r is 3, so this is going to be 9 pi for our area function. And so now we can substitute everything. Our work is going to be equal to the integral from 0 to 9, so that's our height, 9 pi times 1,000 times 9.8 times the quantity of 9 minus y dy. We can go ahead and we can factor and multiply out this constant to make it a coefficient. So if we do so, that's going to be, I'm just going to take 9 times 1,000 times 9.8, all right, and that's going to be 88,200 pi from 0 to 9, 9 minus y dy. Right. Now we integrate, and this is pretty easy to integrate. So we're going to have 88,200 pi times, this is going to be 9y minus y squared over 2 from 0 to 9. Fortunately for us, the 0 is negligible, so it's going to contribute nothing to the sum. And so we're going to get 88,200 pi. We get 9 times 9 minus 9 squared over 2. And in reality, we could just write this as 88,200 pi. This would be 9 squared over 2, right? Because this is 9 squared. So this is 1 9 squared, and this is a half, or minus 1/2 9 squared. So I can just get 9 squared over 2 just to make it easy for us. And so to get a nice exact answer, I'm just going to multiply 88,200 times 81 divided by 2 and multiply it by pi. So we're just going to take that number, multiply by 81, and then divide by 2. All right. And so what we end up with as a precise value, we're going to end up with this 3572100. So 3572100 pi, and that's going to be in joules for the work. All right. Converting into scientific notation. And again, if we were to approximate this, right, we could just multiply it by pi. So I'm going to multiply it by pi. All right. And so that's going to give us this 11,222,083. So this is going to be 11,222,083.118 joules. All right. And of course, we could put it in the scientific notation if we chose to. All right. But I'll just keep the precise value for this. All right. But just making sure we understand like an approximation. All right. Now, that's for part A. For part B, it says, is it true that it takes half as much work to pump the water out of the tank when it's half full? All right, so half full would be where I'm going to call this h sub 1 is going to be 4.5 meters. All right, so let's just figure out that integral. And we're just going to take this. Right? Now, we still have to keep the 9, right? Because the height of the tank is 9, but it's only half full. All right, so in this case, when we approximate it, we're still going up 9 meters. All right, it's just going to be that the fluid is only going to go from 0 to 5, 4.5. All right, so this is going to be equal to our 88200 pi integral 0 to 4.5. And then we're still going to have the 9 minus y dy. All right, so now this one's going to be a little bit different when we compute it. All right, just because we're going to have a 4.5 square. So this is going to be 88200. Same integral, 9y minus y squared over 2, different bounds. All right, so it's going to go from 0 to 4.5. So now we're going to substitute 4.5 back in. So 88200, I lost the pi. All right. And that's going to be 9, 4.5 minus 4.5 square over 2. All right. So I'm just going to compute this inside the parentheses really quickly. All right. And so we're going to get, clear all this. So we're going to get 9 times 4.5 minus 4.5 times 4.5 divided by 2. All right, so this is 20.25. Okay. And we verify that just to make sure. All right, so we have 9 times 4.5. All right, so sorry, it's just this weird calculator. So 40.5, right? And then 4.5 squared over 2. So we have 4.5 square. So it went to the square root of 4.5. That doesn't help at all. So 4.5 times 4.5. And then we're going to divide it by 2. All right, so that's going to be 10.125. All right, and that's clearly going to be 30.375. All right, so good thing I checked it. Not sure why calculators sometimes have that order of operations. Maybe I punched in a number wrong or something, but I'm fairly confident it's 30.375. So finally, we're going to take 88200 pi, multiply it by 30.375. Right, so let's go over here. So we have our 88200 multiplied by 30.375. All right, and that's going to give us 2,697. This is 2,697 or 679, excuse me, 275 pi. All right, now the question was, is that half as much? So if we multiply that by 2, okay, we're hoping that it's going to give us this animal right here, the 357. So this is 3,527,000, etc. This is half of that, okay, or supposedly half of that. Right? And so if we multiply that out, so if we multiply that by 2, so I'm just going to take that number, I'm going to multiply it by 2. All right, that's 5 million. Okay, so twice as much would be 5,358,150 pi. And these are both in joules, by the way. And clearly, that's not equal to this amount right here. Okay. And as you would suspect, it takes a lot more work to pump it out of the bottom, right? So because if we pump it, all right, so let's say it was half full from here, all right, we still have to pump it to the top and get it out of there, all right? But this top layer, okay, so right here, let's say it was this top part, and let's say for theoretically there was like some divider at the bottom, that kind of kept it so that it wasn't pulling. There's not as much distance. Okay, so to go from here to here, it's a lot more distance. And remember, in our formula, if we go all the way back, okay, to the beginning where we derive this, remember, you have to make sure that this distance, okay, so if we go in and we try to multiply the work, the more distance there is, the more work there's going to be, which is why it's not necessarily going to be double, um, um, or I'm sorry, it's not going to be half as much as work to be able to pump it from the bottom of the tank as opposed to the top of the tank. Okay. All right. So hopefully that helps you guys out. And in the last video, what we're going to do is we're going to take a look at one more geometric object for our fluid flow.